All right. Well, thank you very much. I am going to make sure here. So we will start with Newton's idea of gravity, which is very, very intuitive, and it is something that we all could have invented the theory of gravity. Uh, you take a ball, let it go, it falls on Earth. It's very, very intuitive that clearly there is a force on the ball from the Earth drawing it to the Earth, right? So this is a little video clip that we prepared a couple of days ago. You can see a ball falling toward this object sitting at the center, and Newton will tell you that's because there is a force of attraction between the ball that was dropped. I'm going to run it one more time. There's a highly intuitive version of the force of this object at the center attracting the ball, making it go around. Einstein's version is looking at the same thing but completely different. And according to Einstein, there is really no force acting on the ball, but what is going on instead is that the objects distort space-time. So how many of you would like to slow down time? How many of you would like? Well, I see many people raising hand that you would like to slow down time, but you feel that you have no control over time. See, Einstein's theory gives you a lot of power. It says that you can control time. My daughter is sitting in the audience here, it turns out, didn't really know. So she is here in the audience. I would love to slow down time and let it never grow to become a teenager, you see. How many of you would like that? But we have control over time, but it does take a lot of effort to slow down time. But here is Einstein's theory, completely looking at the same thing, but completely different way. And to do that, we have this demo here, but for this demo, I do need a number of volunteers. Maybe 4 people, possibly, if you could come forward, that would be great. One of you, 2 of you, both of you, we can make use of it, of you. If you could come forward, and we could also, I need some people to just hold this thing. This is not terribly stable. Just please hold it and don't let it go. One of you, if you are willing to come and participate. This is being projected here on the screen. I hope that it works, but the light system is such. If I were to place, this is a flat piece of fabric standing on an aluminum frame. This is what it is doing is, what this is supposed to be is space. And the space can be distorted by placing object on it. This fabric, if I were to place a ball, you see the fabric now has dipped. The fabric has pushed, the ball has pushed on the fabric, and there is a little dip here in the fabric. Space has been distorted. And if I were to put a larger ball such as this, which I'm going to do, and you can help me by going maybe underneath and making sure that I can place it in the middle, if you do not mind doing that. So now, I have placed a ball. There is a big dip now here in the middle, and Einstein tells you that there is really no force of attraction between objects. What is instead is going on is that this ball that I have placed here has distorted the fabric of space-time, and when I drop this ball, I hope you will see that this is going around it, not because of any force of attraction. because the space-time fabric has been distorted, and this ball that I placed, which I'm going to do a few more times. So I have a tennis ball going around, and you can see it's going around, and it is simply following this curvature, the distortion in space-time. That's what Einstein tells you. So we will do that with a few more. And if you have another volunteer, let's do another one. So we have another tennis ball, and I have got a whole bunch of marble balls that now I'm going to try out, and let's see if it projects. So now we have got a whole. You are welcome to come afterwards and play with it. You will see that it's a completely different description of the same thing. Now the ball is following this curvature in the fabric. That's what Einstein is telling you, is that no force of attraction, but distortion of space-time. You have Einstein's theory gives you complete power over space and time. You can distort space by placing objects. Of course, you have to place more and more massive objects if you want to distort it more and more. But that's what Einstein theory tells us. The question is, who is right? Is Newton right or is Einstein right? Now, you know, we wouldn't be talking about Einstein's theory if it was not correct, right? So you know already the answer. Einstein is correct. And we have got so many experiments verifying and proving Einstein's theory. But I want to share one experiment that you are all very familiar with. And that is, how many of you use the GPS systems? Raise your hand if you use GPS systems. Quite a few I see. How many of you maybe not use the GPS system, but you have got location service on your smartphone or your tablet? Anyone who does that? Many people do that. So a lot of you see you are making use of Einstein's theory of relativity. And here is the way you do it. The way the GPS system works, the GPS system works is that we have got these satellites about 20,000 kilometers up there in space, and there are 31 of these satellites. They transmit information, the time of the signals that is being sent, and some coding. And your GPS receiver receives this signal, so it tells the GPS receiver what time the signal was sent. The GPS, there is a clock inside of the GPS. It compares the time that the signal is received and the time the signal was sent. The difference between the two tells you how long did it take for the signal to come from one of these satellites to your GPS receiver. And here is a very simple idea for how the GPS system works. And I can use 2 volunteers if 2 people are willing to come. It is a completely safe demo. I'm just letting you know. I can almost guarantee, not 100%, there's never 100% guarantee, but there is a good 99% guarantee that if you come to this stage, you will probably go back quite all right in the same way. Maybe a little wiser, but that's about it. So if 2 people are willing to come to the stage, I would like to have 2 satellites. So you are GPS satellite number 1, if you do not mind standing here. And you are GPS satellite number 2. If you could please stand here and hold this thing. You are GPS satellite number 2. What we are going to do, you are sending a signal. See, you are sending this coded signal, and hold this one end of this thing. You send the signal. I receive. I am the GPS. I got the GPS. I'm GPS user, so I have got the appliance. And you stand here. If I pull on you, do not move. That's the only thing that you need to do. Good.
Should I pull back?
No, yeah. Just stand there. This is a good spot. You are doing absolutely great. So you stay there. So you see, she is sending the signal. I'm receiving the signal. The time difference between the sending time and the receiving time tells me how long it took for the signal to come from you. And what is your name?
Lori.
Lori. So how long it took the signal to come from Lori to me, which is in fact GPS satellite number 1. Lori, also known as GPS satellite number 1. Now, from this you see, I know where I am, how far I am from Lori by taking this time, multiplying with the speed of light that tells me how far I am. Stay there. If I'm pulling you, so I could be. You see, the trouble is,
just shifted my weight.
The trouble is that I could be anywhere here because it is going to take the same amount of time for the signal to go anywhere here. In fact, I can go around in a circle around Lori, GPS satellite number 1, and I have that. Now, so that is not, doesn't give me enough information to tell me where I am, right?
Right.
So what we have to do is get a signal from GPS satellite number 2. And we have got GPS satellite number 2 here. So now what we are going to do, you see, I again do the same thing. Calculate how long did it take for signal to come from GPS satellite number 2 to me. Let's hold it still here. So I'm here, but you see, this is, if I were to stand here, then I know that, no, stay here. I know that this, you see, string is not, it's loose. So which means that I'm not really at the correct position. If I have to move, I have to move, I have to move, I have to move. Now here you see, I am at the correct position where the signal is coming from satellite number 1, satellite number 2, and here I am, I know my position. It couldn't be here, it couldn't be anywhere here. All of these things that were a possibility. Now there is one possibility here at this, and there is another possibility on the other side. That I could be, but if I were to try to go there, I'm likely to. So with that, you see, it takes signal, you need signal from 3 to 4 satellites to pin down where you are. Let's thank Lori and Alice. So that is how GPS satellite works. With this idea, now here is the thing, that we took this string and stretched it and took the space and time to be flat. But Einstein tells you, wrong, wrong, wrong. That's not right. Space is not flat. It's curved. It's curved because of there is Earth there, there is Sun there, there is Moon there that has curved your space-time. So if I didn't correct for the fact that the space is curved, space-time to be precise is curved, I would be making a mistake by taking this string and stretching it. I have to correct for the curvature. If I do not do that, here is what happens. Here is the trouble. If I don't do it, if you don't do it, then because of the curvature of space-time, in one day, your GPS position will be off by 10 miles, which means you wouldn't know whether you are on the north side of Austin or south side of Austin. Is that any good? Is that receiver any good? It's completely useless. So you see, the fact of the matter is that every single time you are using a GPS device or your smartphone to find your location, you are making use of this discovery of Einstein that space and time are curved. And that is being corrected by your receiver and by the satellite signal, and you get your position to an accuracy of not 10 miles, but a few feet. You can determine your location. But to be able to do that, we have to correct for the space being not flat. So that's one application that you all make use of, but not knowing that you are making use of. There is another prediction. There are many, many predictions of Einstein's theory, and there are many, many uses of Einstein's theory. I'm just going to tell you about a couple of them. One of them is black holes. That there are black holes. That follows from Einstein's theory, and there is a ripple in space-time that can go from one place to another place. That's another prediction of Einstein's theory, and we see that happening. Black holes. So what are black holes? Well, these are, as the name suggests, they are black because even light is trapped. The curvature of space has become so large. The curvature of space and time has become so large. I'm going to use my pointer. Rachel, this is more powerful. You see? All right. So you see here, the space and time really have been warped to an extent that even light cannot escape, and hence the name black hole, because anything that falls here comes to the edge, it will fall into it, and nothing comes out, nothing. Okay, so for instance, if you got your used TV, your used, for instance, appliances, your iPhones and iPad and all that thing that is eating up your time, you know where to put it so that it never will come back to you. Okay, all right, so all right, but you see, black holes, these are what black holes are, and they are really something that we astronomers know they exist. It's not a theoretical idea anymore. Black holes are as real as any stars are, and we see black holes in every single galaxy. This is a photograph which shows a not really a black hole because you can't see, but what you can see is the activity associated with the monster. The black hole itself is invisible, but if you have got a monster, you know there is a mischief associated with the monster, and you can see that. And what the monsters do, they eat gas, they eat stars, and they spit things out. And you see this big jet of gas coming out, moving close to the speed of light. Very, very powerful. They can outshine this small part of space or region can outshine hundreds of billions of stars brightness in the galaxy. And so this is something that astronomers have seen for now 50 years. They go by the name of quasars. But we also see black holes in our own galaxy. These black holes here, they are monstrous black holes. They weigh a billion times, tens of millions or billions of times the mass of the sun. And these black holes, by the way, I should tell you, in case you find black holes scary, I can tell you these black holes are really gentle giants. If you got a black hole, if you have to fall into a black hole, choose to fall into a black hole which is really giant. 10 billion solar mass, great. Because you know, if life is going to end, you might as well enjoy the ride. And with big black holes, the good thing is you will enjoy the ride for about half an hour. And I tell my students that if you ever find yourself in the situation where you know you're falling into a black hole, do the following thing. Just remember, if you forget everything that I teach, that's fine. Remember one thing. If you're falling into a black hole, turn off your engines and relax. Because that's the best way that you can prolong your life. Say your prayers and relax. There are black holes which are seeing, you are seeing this animation here. A black hole, see, the black holes are black, but if there is a companion, then there is a chance for mischief. What it will do is that it will take gas, it will draw gas from the companion star, and that gas will fall onto the black hole or into the black hole, but before falling in, the gas becomes very, very hot and produces prodigious amount of emission or radiation, mostly in the X-ray. So you see a lot of X-ray coming out from an object that you cannot see. Black hole, black objects. And a lot of radiation coming out. That's a telltale sign that you are witnessing, not seeing per se, but witnessing a black hole and its mischief. Black holes are born in many, many different ways. Usually, it turns out death of something is birth of something else. That's also true for the stars. Stars are born, stars age, like us, they also die. And sometimes the stars die, leaving behind a black hole. And sometimes two stars collide and turn into a black hole. This animation here, so you will see two stars, in this case neutron stars, coming together, colliding and turning into a black hole, and you can see the fabric of space-time being spun up. It's kind of a whirlpool, you see, is being churned. The space-time fabric is churned in like a whirlpool. And that is, we'll do one more time. You can see. That's, you're witnessing the birth of a black hole. There is a big effort on the part of the United States, our country, and also on the part of Europeans and other countries to find this ripple in space-time. And this is an example of an experiment that is being carried out in Livingston, Louisiana, and also in Washington. This big arm is 2.5 mile arm, and all there is really is a mirror here and a mirror here at this end. And it's looking to make a measurement of the distance between these mirrors by this ripple and how that is changing with the ripple in space-time passing through. That's what it's trying to do. It hasn't detected anything yet, but it is expected to find something soon in the next few years. And when it does, you will see a big headline in all the major newspapers in the world of this particular discovery, and certainly it will be awarded a Nobel Prize. Now, if you have wondered, I talked about falling into a black hole for a person that we have not seen. The nearest black hole may be, 10 light years away. So it's kind of a little far away, but we do see something else. We have seen a number of times a poor star wander a little too close to a black hole and being eaten up. That, believe it or not, does happen. In fact, I will tell you something. Let's first watch a little animation clip of a poor star getting a little too close to a black hole. So watch it. There is a black hole. You can't see anything. There is a little black hole lurking. This star, completely unaware of this existence, comes and just watch. See, it's eaten up, digested, and part of it is spit out, just like the monsters do. But these are real things. And as I say, I told you, I will tell you how often does it happen? My God, during the course of a beer that you drink, you know what you have done? You have led one of these stars to its demise, eaten up by a black hole. So the lesson isn't that necessarily that you should drink less beer, but the fact is that universe is huge, big place, and these things really are going on all the time. So with that, I would like to stop. And just those were a few things I wanted to share with you about Einstein's theory of relativity, how cool it is, how empowering it is. You have control over time, by the way. As I say, I wish that we can control time, but one way we can control time is, for instance, some of you may have seen Interstellar, and this is not an advertisement for Interstellar. I'm not telling you to go out and see Interstellar, but those of you who have seen know that you can slow down time by going close to a black hole. That's one place where the time slows down. So all you have to do is go fast, really go fast. Close to the speed of light, you can slow down time. Or you can go close to a black hole, you slow down time. And those are two completely verified ways we know how to slow down time. So in case you were ever wondering, my God, the day is going so fast, the week is just running, and the life is passing by, you know what to do. All right? So with that, I will stop.